3 men were dying 250,000 miles from Earth, and the thing standing between them and suffocation was a folded piece of cardboard, 2 strips of duct tape, a spacesuit hose, a plastic bag, and a sock. That is not a metaphor. Those are the actual materials. But here is what most retellings of Apollo 13 get wrong. The sock was not the miracle. The explosion was not even the beginning of the real crisis. The moment that nearly killed Jim Lovell, Jack Swigert, and Fred Haise happened not in space, but 5 years earlier in a subcontractor's office, when a single voltage number was written down wrong and nobody caught it. This is Apollo 13 from the explosion onward. Every engineering decision that kept 3 men alive. And it gets worse before it gets better, because it has to. Apollo 13 lifted off on April 11th, 1970, at 1:13 p.m. Houston time, carrying Commander Jim Lovell on his 4th spaceflight, lunar module pilot Fred Haise on his 1st, and command module pilot Jack Swigert, a last-minute replacement who had joined the crew just 3 days before launch, after a measles scare pulled the original pilot. Their destination was the Fra Mauro Highlands of the Moon. 46 hours into the flight, Mission Control radioed up, "We're bored to tears down here." 9 hours later came the explosion. Understanding what exploded means going back to 1962, when Apollo's oxygen storage tanks were first designed with internal heaters and thermostats, safety switches rated to cut power at 28 volts, matching the spacecraft's operating voltage. 3 years later, in 1965, NASA upgraded its ground service equipment to 65 volts for efficiency. Engineers updated relevant components throughout the system. But the thermostat inside oxygen tank number 2 carried a classification of not flight critical, because it only ever ran on the ground, so nobody flagged it for the upgrade. It stayed at 28 volts in a 65-volt world, and nobody caught it. In October 1968, that same tank was being removed from an earlier spacecraft for refurbishment, when a technician left one of 2 bolts fastened. A crane lifted the assembly. The shelf hinged upward about 2 inches, and engineers who inspected it afterwards saw no obvious damage and reinstalled it. What they missed was that the internal fill tube had almost certainly been knocked loose, and that detail would matter enormously. 6 weeks before launch, in March 1970, technicians discovered the tank would not drain after a fueling test. Rather than replace it, which would cost time, engineers chose to boil the oxygen off by running the internal heater continuously for 8 hours. During those 8 hours, the 28-volt thermostat tried to open as designed, but 65 volts welded it shut. The heater kept running. Temperature inside the tank climbed to roughly 1,000 degrees Fahrenheit, and the gauge only read to 85 degrees, so operators saw nothing unusual. Teflon insulation on the internal stirring fan wires charred, cracked, and split, leaving bare copper conductors sitting in a sealed chamber of pure oxygen. The tank was then fueled, installed, and loaded onto Apollo 13, where it flew 55 hours and 54 minutes before anyone touched those wires again. At 55 hours, 54 minutes, and 53 seconds into the mission, Swigert flipped a switch for a routine cryo stir. The bare wires sparked, Teflon ignited, pressure spiked past structural limits, the tank dome failed, and one full panel of the service module's hull blew off. Swigert: "Okay, Houston, we've had a problem here." Lovell repeated it. "Houston, we've had a problem. We've had a main B-bus undervolt." An undervolt A power fault was the first readable symptom, not an explosion. The crew felt a bang and a shudder, and their instruments started failing. Within 3 hours, both oxygen tanks in the service module sat empty. Without oxygen, 2 of the 3 fuel cells, which converted hydrogen and oxygen into electricity and water, died immediately, and the 3rd followed. Without fuel cells, no power, no water. The main engine at the back of the service module, supposed to bring them home, now had to be treated as suspect because the explosion had happened in the adjacent bay and nobody knew what the blast had done to it. In under 15 minutes, Apollo 13 had lost its oxygen, its power, its water supply, and its primary engine. What it still had was the lunar module. Aquarius, call sign for the lunar module, was a separate spacecraft attached to the front of the command module, with its own power, its own oxygen, its own propulsion. Designed to support 2 astronauts for 45 hours on the lunar surface, it now had to keep 3 men alive for 90 hours in deep space, stretching the lunar module's batteries across twice the time. And for 50% more people, meant cutting electrical consumption to roughly 1/5 of normal. Heaters off, computers off, displays dark. Temperature inside Aquarius dropped to 38 degrees Fahrenheit, just above freezing, and water rationing fell to 6 ounces per person per day, about 1/5 of what a person actually needs. Fred Hayes, already developing a urinary tract infection from dehydration, lived in that environment for the next 4 days. The crew moved into Aquarius at around 58 hours into the mission, and the command module was powered down. Now stop here, because this is worth sitting with. At this point, the crew was alive. They had a lifeboat. Mission Control had stabilized the immediate situation. The worst, you might assume, was over. It was not over. The most dangerous problem of the entire mission had not been recognized yet. Every person exhales carbon dioxide, and in an enclosed space it builds. The LM absorbed it using canisters packed with lithium hydroxide, a chemical that neutralizes carbon dioxide. Those canisters were sized for 2 crew members over 45 hours. 3 people generate 50% more carbon dioxide, and the canisters were running out fast. Plenty of spare canisters sat in the command module, but the CM canisters were square. The LM slots were round. Same chemical, incompatible geometry. Mission Control watched the carbon dioxide partial pressure climb. Safe, breathable air sits near 0. At 7.6 millimeters of mercury, the LM's amber warning light would trigger. At 15, cognitive function deteriorates seriously. The LM's reading reached 14.9 and was still rising. Roughly 38 to 40 hours remained before the air became incapacitating. Ed Smiley, chief of the Crew Systems Division, assembled a team, roughly 60 people by his own later account, and the constraint was absolute. Every piece of the solution had to come from materials already aboard the spacecraft. Nothing could be sent up. Here is what they designed. Take 2 square CM lithium hydroxide canisters, wrap them in plastic bags from spacesuit stowage. Use the cardboard cover of the flight plan as a flow baffle to force cabin air through the chemical rather than around it. Connect a spacesuit umbilical hose to the inlet, seal the hose junction with a sock, hold the whole assembly against the bulkhead with a bungee cord, and bind it together with 2 strips of gray duct tape. Mission Control called it the mailbox. Capcom. Joe Kerwin read the instructions aloud. Swigert and Hayes built it in about an hour. before the mailbox, the carbon dioxide reading stood at 14.9 millimeters of mercury and rising. Within roughly 1 minute of the changeout, it dropped to 4.5 and kept falling. For the remaining 47 hours of the LM's operation, carbon dioxide held between 0.1 and 1.8, well within safe limits, maintained there by cardboard and a sock. The carbon dioxide problem was solved. The power problem was a different nightmare entirely. Nobody had ever intended to restart the command module from a complete, cold, dark state in deep space. Its startup sequence assumed fuel cells running, systems at temperature, normal voltage, none of which existed. After 4 days sitting at 40 degrees Fahrenheit, moisture had condensed on every surface inside the spacecraft. John Aaron, a flight controller who had already built a reputation as the sharpest electrical mind in mission control, worked alongside Ken Mattingly. The pilot pulled from the crew 3 days before launch, running simulations in the command module trainer on the ground. Together with engineers in the mission evaluation room, they produced a brand new power-up sequence from scratch, doing in 3 days work that would normally take 3 months. To stay within the hard ceiling of what the entry batteries could provide, Aaron made a call that broke procedure. He instructed controllers to bring the instrumentation system up last, in the final seconds before re-entry. That meant controllers would have no confirmation the cold start worked until the spacecraft was already committed to entering the atmosphere at 25,000 miles per hour. The entry batteries themselves had been slightly drained during the initial crisis, which meant they needed recharging, but the lunar module had never been designed to charge the command module. The electrical umbilical between the two spacecraft was built to carry power one direction only, from command module to lunar module. An engineer named Gary Johnson devised a procedure to reverse that flow, trickling power from the lunar module's larger reserves into the command module batteries. It had never been tested. It worked. While engineers on the ground worked through the power problem, the spacecraft still had to get home, using an engine never designed for this purpose, aimed in a direction calculated without the normal navigation tools. Debris from the explosion made conventional star sighting impossible, so someone in mission control devised a substitute. Use the sun itself. Rotate to a predicted attitude and sight the sun through the alignment telescope. And if it landed in the correct position, the navigation platform was still valid. Lovell performed the check. Less than half a degree off. They were good to burn. The critical engine firing, executed 2 hours after the closest approach to the moon, ran for 4 minutes and 24 seconds, added 860 feet per second to their velocity, shifted splashdown from the Indian Ocean to the South Pacific, and cut roughly 9 hours off the return journey. The final course correction ran with no active guidance computer at all, using the visible boundary between day and night on Earth as a directional reference, and Schweigert's wristwatch to time the burn. On April 17th, jettisoning the service module gave the crew their first view of what had happened 4 days earlier. Lovell's words in the mission transcript were, "There's one whole side of that spacecraft missing." Aquarius was released shortly after, and Capcom Joe Kerwin signed off. "Farewell, Aquarius, and we thank you." It burned up in the atmosphere. The command module cold started successfully. Parachutes deployed. At 1807 UTC on April 17, 1970, Odyssey splashed down in the South Pacific, 4 miles from the recovery ship USS Iwo Jima. After a mission lasting 142 hours, 54 minutes, and 41 seconds. Between them, Lovell had lost 14 pounds, Schweigert 11, and Haza 6.5. 31 pounds of body weight across 3 men, stripped away by 4 days of cold and rationed water. The review board chairman concluded that the failure was not the result of a chance malfunction in a statistical sense, but rather an unusual combination of mistakes coupled with a somewhat deficient and unforgiving design. A voltage number written wrong in 1965, a dropped shelf in 1968, 8 hours of overheating in March 1970. No single one kills anyone. Together, they nearly killed 3 people 250,000 miles from home. After Apollo 13, NASA added a third oxygen tank in a separate bay, removed the stirring fans, replaced the Teflon wiring with stainless steel sheathed conduit, and rated the thermostats for both voltages. The mailbox adapter became standard equipment on future missions. Ed Smiley, who led the team that built the fix, died in April 2025 at 95. Jim Lovell died in August 2025 at 97. Fred Hayes is still alive at 92. What kept those 3 men alive was not a miracle. It was 60 engineers working through the night, a flight controller rewriting procedure from memory, and a piece of cardboard taped over a hole in the chemistry. The system failed. The people refused to.